Yep.
All right, everybody, we're getting started again. Apologies for the technical difficulties. We're going to go in a slightly different order because of that. So our first speaker will be Rob Nowak. He's the Grace Waba Professor of Data Science at the University of Wisconsin-Madison and a member of the executive community of IFDS, which for those of you who don't know, is the Institute for Foundations of Data Science. His vast array of work on sparsity and active learning, learning networks, and interactive machine learning has been showcased at a wide range of venues, including top-tier machine learning conferences. So why don't you take it away?
Great. Thank you. Can everybody hear me okay? All right. Well, thanks. And thanks to Emmanuel for a great talk. I think there's going to be some commonalities that you'll see in what I'll talk about too. I picked the topic for today of label-efficient learning in the age of foundation models. And one of the main reasons I picked it is it's a nice showcase of collaborations going on between UW-Madison and the University of Washington, Seattle, which form two of the core teams of our IFDS Institute. We also have a few people from Georgia Tech, Steve Mussman, who was a IFDS postdoc, and then a few people at Stanford, MSR, and UC Riverside. So it's a real team effort, the work I'll describe. It also is nice for tripods because it kind of showcases how we brought together a lot of ideas, new and classical, from statistics, optimization, and machine learning to, I think, make some good progress on this idea of label-efficient fine-tuning of big models. Okay, so this first slide is just to kind of show you the usual pipeline for machine learning. You have a lot of raw, unlabeled data. Somehow you have to get a training set. And you do that usually requires some amount of human labeling or annotation. And that can be a big bottleneck in the process. It's time consuming, it's expensive. And so we're looking at ways to reduce that part of the process. So what I'm going to do first is just go over some of the really basic ideas of kind of label efficient learning classically. And the first starting point would be coming from statistics, which is experimental design. And the basic idea here is somehow you're going to use the structure of your unlabeled data set to select a good subset of points for labeling. And I'm going to illustrate this in a situation where there's some sort of cluster structure. So I think if you look at these gray data points, they're gray because we don't know what their Y values are yet. They're labels. But you can kind of make out some geometrical structure. There's some clusters. And so an idea you could take here, if you could see those structures, is to say, oh, well, I'll just get one example from each cluster, label it. And now if I think those clusters are homogeneously labeled, I'm pretty much done. And this idea goes back, one of the nicest little results on this is due to Castelli and Cover. They say if the clusters are discernible from the unlabeled data, then one labeled example from each cluster yields a near optimal classifier. And that's, again, assuming that the clusters have homogeneous labels. So there's a theory to support this kind of idea of experimental design. Maybe the next step you would think about is something that's called semi-supervised learning. Here, the idea is that you might have a very large unlabeled data set, capital N unlabeled samples, and then little n of those are labeled for you. And the idea is that somehow you're going to use the labeled examples and then exploit the structure of the unlabeled data set in order to do better. So let me kind of just illustrate this with pictures. So suppose I just have a small number of labeled examples. 3 in this case, and I want to learn a linear classifier. Well, it would go here. That would be like your max margin support vector machine type of solution. But now, suppose I reveal to you all the other data that I have that weren't labeled. And you say, well, wait a second, that doesn't look right. I should adjust things like this, right? And so that's the idea of semi-supervised learning. And a kind of little theoretical result on this says that if the certain clusters are discernible from this large unlabeled data set, but if you can't really see that structure from just looking at the labeled examples alone, then semi-supervised learning is going to give you a big boost. Okay. Another approach, taking it one step further, is to what people call active learning, or in statistics and so forth, this we call sequential experimental design. And here the idea is you're not just going to look at the unlabeled data to decide which examples to label. You're going to label some, look at the unlabeled and labeled examples together to decide which to label next. And a nice way to illustrate this is just, again, with learning a linear classifier. The gray points aren't labeled. The red and blue are our labeled examples. This is the best linear classifier we have so far. Passive learning would just say, pick another example that hasn't been labeled yet, label it, and try to improve your classification rule. You could see that in this case, that purple one that I circled probably wouldn't be very helpful because it's sort of surrounded by other red ones. A better idea might be to pick an example close to your current decision boundary, which is one way of kind of measuring how confident or certain you are about the predicted label there. And that's what one technique for active learning would be. And then the idea is that maybe with active learning of this nature, I can learn a much better classifier with a better error rate with a fewer number of labeled examples. And there's nice theorems about this too. If the model class has a finite VC dimension, then the active learning rate decays exponentially with that dimension, but the passive learning rate only goes down polynomially. So there can be, in certain nice situations, an exponential improvement in label efficiency using active learning. And then finally, I just want to, let me back up a little bit. I don't know if I can. Okay, yeah. Combining two things together, sort of this semi-supervised learning idea with the active learning idea. One way you could do this, a kind of common approach to semi-supervised learning, classically speaking, is to construct a nearest neighbor graph and then use the structure of that graph to figure out how to predict or impute labels of examples you haven't seen. And so here I'm showing you unlabeled examples with a few labeled examples and then the nearest neighbor graph of these data. And an active learning procedure could be doing something like a generalized binary search on this graph to kind of quickly identify where the decision boundaries or cuts in this graph should go. And then once you have separated the graph into components, you can just propagate labels using your favorite approach, nearest neighbors, or some sort of graph Laplacian or whatever. And people have studied this too. There are theoretical results that say something like if the cut set of this graph consists of m edges, then order m labeled examples are sufficient to accurately label the entire data set. So these are some of the main kind of classical approaches people have taken to say, well, do we really just want to pick a random subset of our data set to label and then train our machine? Or do we want to somehow be more systematic about deciding which examples to get labels for? Because again, getting labels is an expensive bottleneck in the process. So are those kind of classical ideas pretty, yeah, good. Okay, so now let's go to what we're doing now. We would be not using little graphs or linear classifiers. We'd be using huge, ginormous pre-trained models. And so the idea is that I take some great data set like CLIP, which is images with text, and then I can use that image plus text data set to train a neural network and get really good feature representation. So the idea is I have some giant neural network, and what comes out then is now a model F that takes images, for example, and produces some sort of representation of those images in a nice embedding. We can think of these as sort of optimized features that have been extracted from raw images. And so what you should think about maybe just kind of at a high level is going on is I would be starting off with my raw data, which are kind of a mess. I'm showing like two classes here, but you can see they're all jumbled together. Not a lot of nice structure. But after I transform these raw images into these optimized features, maybe what's going on is something more like this. It automatically starts to kind of cluster some of these things together, priming the pump, so to speak, for now doing something more efficient. And so the idea is that these label efficient learning methods, experimental design, active learning, semi-supervised learning, they don't really work very well, or they're pretty ineffectual if you're just trying to train a giant model from scratch. You're just not going to see much of an advantage over just picking examples at random for labeling and training. However, once you kind of take a pre-trained model that already is giving you some interesting and useful structure to exploit, then these label efficient methods can be really effective. And so that's what I'm going to kind of explain and talk about. So the high level idea is we're going to take insights that we've learned over the years from the classical methods, the theory, the approaches and so forth, and then combine that with these pre-trained models. I'm not going to go into all the details about how we integrate those theories with modern techniques, but I'll show you some of the experimental results and try to give you a little bit of a sense for what's going on. Okay, so let me just give you one example of this. This was something we cooked up just to illustrate how effective this could be. So we took ImageNet, and there are about 0.1% of the images there are tiger sharks, apparently. And then we say, well, let's just train a neural network to predict whether an image is a tiger shark or not. And what I'm going to look at here is the percent of data labeled, and then also the accuracy that we get. So if we just take all the labeled data and train our tiger shark detector, we get almost perfect 100% accuracy. And then you can say, well, okay, but what could we do if we didn't label all the data? And there are a lot of companies and other things out there that are saying, hey, we can do label efficient training set designs so that you don't have to label all your data. And those are just a few of the companies, but basically they're kind of like doing active learning, semi-supervised learning, et cetera, from scratch, trying to train a big vision model from scratch. And that helps a little bit. You can maybe reduce the amount of data that you need to label to 50%, but not much more. Whereas if you take this idea of a very large pre-trained model, like clip-trained model, and then combine that with graph-based active learning and semi-supervised active learning ideas, you can actually get like a much bigger improvement. We can label just 3% of our data and get almost 100% accuracy. Yeah.
I guess a particular example, like clip might also be trained on ImageNet already.
Yeah, the question was, is clip trained on ImageNet? Probably somebody else could answer that better for me. I should also say I'm not 100% sure that we use clip here. I was just kind of using it as an example, but ignoring that little issue, let's just assume it wasn't. I don't think that would really affect things too much here because there's so much data anyway in clip. But yeah, I take your point. Maybe there's some sort of leak of information there, but yeah, I think that is still representative of what can go on. Was there another question, or was that the same question? Same question. I mean, we can talk about it offline, but we can talk to my student Gfan, who's knows a lot more about some of these details. Okay. Yeah. Another question. Yeah.
3% would be very small, so maybe like, but you have a lower bound there, right? You cannot go beyond that, so that.
Yeah. So that what's going on here is really that obviously you're going to have to somehow figure out a way to cleverly get some tiger sharks into your training set, right? And so one of the things that makes this kind of amazing improvement here is just the fact that you're in a very imbalanced setting. And that's one place, and I could give a whole talk about learning when you have very imbalanced classes. It's a super important problem. It comes up all the time, not just in multi-class, but especially in things like multi-label classification. And so when you have very imbalanced data sets, then active learning and things like that can be really, really helpful because you just want to upsample those rare classes. So that's part of what's going on here. Okay, so now I kind of want to go into what we're doing today. And I want to, first of all, kind of give you some examples of what are the modern approaches to label efficiency. And I think there are kind of three that are really important. One is using large pre-trained models like CLIP that I talked about. Basically, this is what you might call transfer learning. Like, we have this great model, it's doing all sorts of good things, and we can use that, we can transfer that pre-trained model so that it's almost giving us that one shot or zero shot kind of performance on new data. But probably zero shots asking a little too much, maybe you want few shots. So that's where the active and semi-supervised learning comes in. So semi-supervised learning, one of the kind of recent kind of approaches that work very well with large models is something called flex match. But again, all this is doing is somehow exploiting geometric structure of embeddings to impute labels. And then active learning, a state of the art there is something called badge, where they're taking a deep learning model and labeling examples with large loss gradients, which are sort of these large losses, and the large loss gradients would be indicators of prediction uncertainty. And that can be very effective, or at least can be effective. I shouldn't say very effective, but can do something. Okay, so we have pre-trained models, transfer learning, semi-supervised learning, active learning. These are some of the ingredients we want to put together when we're trying to fine-tune large models. And so that's what our goal is of this work of the team I had up at the beginning. We want to study the integration of these methods along with using the insights we have from classical theory to achieve greater label efficiencies. So this is what we call the label bench project. So let me kind of give you a picture of the label bench paradigm or setup. The idea is we have a pre-trained model, which is taking our raw data to some embedding. And then we have a kind of box here, which is sort of really where we're doing our experiments. We're saying, well, how can we integrate active learning, semi-supervised learning, and so forth, test out lots of different algorithms, different combinations of algorithms in a way that's scalable and doable. And so one of the key ideas there is that active learning can be expensive because every time you collect a new set of labeled examples, you're retraining a model in order to decide which examples to take next. So we don't do full retraining. We're just going to retrain a shallow model on top of the pre-trained model, a linear head or a small neural network on top of that model. And then we're using that plus semi-supervised learning to impute many labels. And what's happening then at the end is we get out of this a partially labeled data set, and then we'll finally fine-tune the full model just once at the end. Okay, so this is something that is lightweight enough so that we can, again, try out many different algorithms, different combinations of algorithms to see what really works. And I just want to give a shout out here to Jifan Zhang. He's a PhD student working with me. He did his bachelor's and master's work at the University of Washington with Kevin Jamison's group, and then he came over to me. So it's another, he actually is like really an IFDS guy, and this has really been all his idea. He's leading the team. I'm just kind of support. Okay, so let me kind of tell you, we're going to first look at how this plays out in the case of vision models. And so the first insight we have is that we actually can get really large improvements using active learning, semi-supervised learning in terms of label efficiency. And the reason it's kind of new and exciting is that's not what we were seeing before. So let me kind of say what we were seeing before. So this is kind of looking back where people were looking at things like this badge algorithm that I mentioned and other things. And they said, well, badge is great. Look at on CFAR 10, we get a little bit of a gain over passive learning. And the gain is maybe 10% label saved. And you'd be like, wow, 10% of my labels. I instead of having to label 100, I only had to label 90. That doesn't really, there's a lot of effort going into doing this active learning. It doesn't seem worth it, right? Oh, I got 5 minutes. Good, I'll be good. Okay, and then here's what we're doing now. We're again taking a large pre-trained model. They were training a model from scratch. We're not doing that. We're taking a large pre-trained model. Then we're doing semi-supervised learning, active learning, and so forth. And now we're getting like 70% label savings. So a much, much more significant gain. And that's sort of one of the insights. You really want to start with that pre-trained model. You don't want to try to use these methods to learn a model from scratch. And just kind of why this makes sense, label efficient learning methods don't give you much of a gain if you're trying to learn models from scratch. Like a baby, maybe you should try to expose a baby to a lot of passive learning. They haven't learned how to learn yet, right? But if you take a college grad, they're already pre-trained. They're primed to learn. So label efficient learning can work really well for them. Another insight is that really this combination of active learning and semi-supervised learning is important. A lot of work just says, oh, we're going to focus on semi-supervised learning, or we're going to have a new active learning algorithm. And we're saying, well, you know, what would we really do if we want to make progress? We combine all the best ideas together that we know about. And so we see that there's a big lift from combining not just active learning alone, but plus semi-supervised learning. You'd see the same sort of thing, vice versa. They're kind of complementary to each other, and they really work well together if you integrate them. And then finally, I just wanted to say that another thing that, you know, I said people worked really hard to develop the best active learning algorithm for deep learning systems. Badge would be an example of that. But what we see once you start with, take the pre-trained models, combine with semi-supervised learning and so forth, you kind of don't have to work so hard. The simplest thing, which is margin-based sampling, which is just sample near your decision boundary, works as well or better than all the fancy methods. So that was another kind of takeaway from all this. Okay, and then in the last 2 minutes, I'm just going to say a little bit about what we're doing now. We're trying to look at large language models and supervised fine-tuning there. You have prompts. You're going to need to get some human responses to a subset of prompts so you can fine-tune your language model. You could do that randomly. You could try to do it actively, or you could do something with experimental design. We're taking an experimental design approach because active learning is just impractical. You can't even retrain once, right? It's just too big of a model. So we're not doing that. We're just doing experimental design, which again is just trying to say, get a good representative set of prompts. But what do you mean by a good representative set to label? So we looked at, I'll just have one more slide here with some results. We compared within Label Bench a bunch of different experimental design techniques. I'm showing a couple of examples here. Uncertainty algorithm, which is one that is somewhat useful. And then this is some work using submodular optimization techniques for the selection of prompts for labeling by humans. And you can see what we're able to do is we can get basically a 50% reduction in the number of prompts we need to label to get about as good of accuracy if we labeled almost all of them. And so, yeah, and the great thing is there's only one final fine tuning going on here. We're not doing anything that is computationally difficult or prohibitive. So I will just stop there and I'll say, we are seeing big gains in label efficiency when we are fine tuning large pre-trained models. These same label efficient methods aren't really very useful if you're trying to learn models from scratch. So you should always use the pre-trained models. We're using theory methods and insights from classical methods to give us some guidance in how we're integrating these things together. And then this label bench project is an open source project. Anybody can contribute to it and get involved. And it is a nice way, lightweight test bed to kind of experiment with all these different techniques. And I will stop there. Thank you.
Okay, thank you for the wonderful talk. We'll take some questions now. Yes?
So you said for this pre-trained model.
Yeah.
You don't really need the fancier methods like that.
Yeah.
So can you perhaps there's some theoretical justification that in the distribution of the data, you can argue that it satisfies some conditions. That's why
Yeah,
it's important.
I think that picture I had, I guess it was here. Oh, sorry. The pre-trained model is already giving us it's not zero shot,
Right.
but we already have nice structures.
Right, right.
You have
Intuitively,
nice
that's what's happening.
clusters and stuff.
Right.
You just don't
Understand.
have to worry
Right.
so hard.
Yeah, I'm just wondering whether
I
there's
think
some
that's
framework.
my intuition at
Mhm.
least. I mean, maybe there's ways we could test that out, but we are in super high dimensions, so it's a little hard to know for sure. But yeah, I think that's what's happening.
Okay, do we have any other questions?
Suchay?
So for your very last part, I think it's fair to say there's an ongoing debate about about whether active learning is needed for language models as opposed to just a one shot and then so do you have any comments on that based on your experience?
Yeah, I would say I don't think active learning is going to be too useful for fine-tuning language models. And we're not doing active learning, we're just doing experimental design. So it's only looking at the prompt structures and the similarities and geometry of the prompts in whatever embedding. So yeah, I do, and there are theoretical reasons why I don't think active learning would be very useful. Maybe one is that somehow a language model is really about predicting these probabilities, and it's almost more of a regression problem. And there are kind of folk theorems that say that under certain mathematical conditions, the advantages of being adaptive can give you at most a 2x improvement. And I think we're kind of in that regime with language models. So, maybe in some specialized cases, the situations active could be helpful, but generally, I don't think active learning is a great idea for language model fine tuning.
Okay.
Yeah.
All right, let's give Rob one more round
Thank
of
you.
applause.